Right, but I think we're going to rewrite some part of the paper to to.
Call is Weyl optoelectronics. That's what Tom was in
and feedback coefficient. He wants to just measure alpha x, y.
Yeah,
Basically applies a heat current without any electric current, and then measures transverse voltage.
Okay, okay.
So
alpha x, y is the charge current in response to the temperature gradient.
well, there's an Onsager relation between two coefficients.
The other one.
One is voltage in response to heat current.
Right.
So you can do it that way instead.
I see. So, I see. I don't know what's the local Harvard time. I imagine we start 5 minutes later.
Harvard seems to be 7 as far as.
Sorry. Running way too early. 7.
Oh, I mean, you probably know better than I do. All I know is whenever I come to a seminar at Harvard, it's even later than we are.
So I'm going to see Bourne in April.
Okay.
Yeah, there's a celebration for the party for him.
Oh, good.
70, yeah.
Wait, is he 70?
Something like that.
Really?
Yeah. And curious, this, it has all the data on this lattice cylinder. Right?
Yeah.
Both resistivity and feedback. I think also NERS. I think
probably. Yeah.
Again, he can also just reply.
Yeah. Yeah. Good. Good.
Oh yeah. The other thing we should get together is about this the mass. Right? The fact that there is a mass
Yeah.
at low temperature. I think this can explain the upturn of XY. And that could be a good story to add to these experimental papers.
Yeah. In principle, we should do that. And
hey, Bart.
hi.
Hi, thanks for coming over. Yeah. This is sort of deep connection with thermoelectric.
Yeah, this is all about thermoelectrics. So you can experiment.
Device is interesting there. So,
All right.
well, I mean, they're definitely interested in thermoelectric. There's magic beaver.
Oh, great. Yeah. I know. Yeah. I know that there's a lot of industry people interested in quantum materials.
Yeah.
But so far, people I've talked to don't seem to be using some electrics. So up to here.
It's sort of neat that it has to come from the physics. So, I'm interested to see what.
Okay, good. Well, hopefully you're still interested at the end of the talk.
Are you going to do the introduction?
Yeah, I'll do the introduction. Yeah. So this is the second year of the second days.
Oh, no, we're in year 6 currently.
Year 6. Right. From the beginning.
Yeah, so we're renewed. Because 5 plus 5. And then the 5 got closed out just now. We're in halfway year 6. So it's the first year of the second 5. Yeah. And now we can do if they want to. So we can be sort of far out like
Sam. You had to ask about official Harvard time. Maybe they went.
You look a little stressed. You look a little stressed.
Yuanming Liu is going to be here for like a month.
Oh, is that right?
Yeah, where he's a visitor of the Harvard CMSA.
Oh, CMSA. Right. Okay. Well, then.
Have him over sometime.
Yeah. Oh, also, yeah, I got an email. We should also invite this guy up.
Sarang?
Sarang, yeah.
Yeah,
The
he's
question
great.
is when. The problem is my travel starts. But maybe, our semester ends in early May. Yeah, the last several months is quite busy. I've been extremely excited about some work I'll tell you more about. I coined a phrase, super metal. I don't know if I told you.
Super metal. Okay.
Super metal, yeah. I'm super excited about this.
Okay.
So I spent the last several months. But now it's close to completion. And then, but then the semester is coming to an end.
Yeah. Well, we could bring him for like a special seminar right after.
In the summer,
Or right the week or two after the semester.
Okay, sounds good. He's a very nice guy.
He's a very good guy. He's very sharp. I can't talk to him for less. Like if I talk to him for 30 minutes, I'll have some new idea for a paper.
Yeah. He's a great guy.
Very quick. Yeah, Oganessian.
He probably would be interested in this work.
Yeah. Yeah, I told him a little bit about it, but.
Did they hire anyone in the end?
I think it's still going. I mean,
Still going.
I think they just. It's very delayed. Hold on, let me check this microphone. Should I turn this on?
now you're good.
Okay, good. Thank you. Oh, it's even.
Okay, great. It's my great pleasure to welcome and introduce our speaker, Brian here from MIT. So Brian got his PhD from University of Minnesota, working with Boris Shklovsky on Coulomb impurities in semiconductors and many related topics. But this is just a small part of his broad interest. He has written papers on physics of basketball, sports, population dynamics, etc. And also, from, last year, Brian became famous for spotting repeated noise patterns in the claimed high-temperature superconductor, so preventing our field from another Sean scandal. So today, it's a great pleasure to have him here. He will tell us about thermoelectricity in these novel quantum materials. Make the world win again.
Oh, is that too loud? Okay. Hi guys, thanks for coming. Let me see if I can move this. It was a bad idea to wear a t-shirt. Okay. All right, anyway, hi, thanks for coming. My name is Brian, and I'm going to tell you today about thermopower in nodal semimetals. This is actually some kind of exciting work that might actually be useful, which is unusual when you're doing theoretical physics, that you do something that might be useful for humanity, but this is kind of fun. Okay, so this is mostly a theoretical work, and my primary collaborators are Vlad Kozy, who's a grad student at MIT, and Liang Fu, who just was nice enough to introduce me. But I'm also going to talk about some experiments. And in fact, there are two different experiments that I'm going to talk about. One is on the material zirconium telluride, which is a Dirac material. And my collaborators on that are from Peking University, in particular, the group of Xiaosong Wu, and I think in particular his grad student Wenji Zhang. And the group at Southern University of Science and Technology in Shenzhen, and the group of Liuan Zhang, and in particular his postdoc Peipei Wang. And I'm also going to talk about experiments on a Weyl semimetal, tantalum phosphide, and this is in collaboration with the group at MIT, the group of Mingda Li. In particular, I think is his postdoc Fei Han, and then his students Nina Andreevich and Tan Nguyen. Okay. So this is about the thermoelectric effect, and perhaps just to remind you, the thermoelectric effect is the generation of voltage, an electric voltage, from a temperature difference. And the idea is that if you heat up one side of an electric material, electrons on the hot side tend to diffuse a little faster. And as they diffuse faster on the hot side, that makes them pile up on the cold side, so they generate a voltage difference. And conceptually, you can think about the magnitude of this effect, which is called the thermopower, which is the ratio of delta V over delta T. That's the thermal power. You can think of it as a reflection of the entropy per carrier in a conceptual sense. Sorry, I have to apologize for notation for a second. For some reason, everyone uses the letter S for thermal power, despite the fact that it's very closely related to the entropy, which is also S. So in this talk, whenever you see normal S, that's thermal power. Whenever you see this Gothic dragon-looking S, that's entropy. Entropy is the Gothic S. Okay, anyway. But the point is that when you heat up one side of a material, electrons migrate from the hot side to the cold side, and in their equilibrium configuration, what they're really trying to do is equalize the free energy per electron. They're trying to equalize what we call the electrochemical potential, which is something like the free energy per carrier. And we know that free energy looks like internal energy minus T times entropy. And if that quantity is constant, that means when you apply a gradient delta T, the electrons have to set up for themselves a gradient of energy delta U in order to make this thing spatially constant. So if you just make the ratio delta U over delta T, that tells you the entropy S per carrier, right? So in that sense, this ratio delta U over delta T is like the thermopower delta V over delta T. So the thermopower is a reflection of entropy per carrier. And when carriers have lots of entropy, they produce lots of thermal power. Now, this is actually a useful effect, a potentially very useful effect, because it allows you to turn waste heat, something coming off of an engine or a reactor or something, and convert it back into useful electric power. So you put some load resistor here, and you regain some of the lost heat. You can also operate the effect in reverse, where instead of putting a load resistor here, you put a voltage source that forcibly drives the current in the opposite direction, and now your electronic carriers will suck heat away from a cold side, and this is a way to make a refrigerator. Now, this is, in principle, a very practical effect. The way to do this, in fact, is you make a junction of two different materials, say a P and an N material, and you make a junction here. This is a thermocouple. And now it can sort of suck heat away from some heat source. And you have heat flowing in parallel down two legs, even while the electric current runs in series. And so now you put some resistor here, and you generate useful electric power. Alternately, you can run it in reverse, like I said, and now you suck heat away from a junction and you cool down something. Now this is a heat a generator, an electric generator, and the effectiveness of a generator is described by the thermal power, what's called the Seebeck coefficient, which is the ratio delta V over delta T. This thing over here is a refrigerator, and the usefulness of a refrigerator is determined by what's called the Peltier coefficient, which is the ratio between the heat current that is coming in and the ratio of the heat current that you get out to the electric current that you put in. This is called the Peltier coefficient. And it happens that there's a reciprocal relation between these two coefficients, what we call an Onsager relation, that basically says they're proportional to each other. And the conceptual way of thinking about it is that any material that's good for making a generator is also good for making a refrigerator. So it's the same goal. Now, if you want to make something practical, you make many of these junctions and you pile them up in some stack. And in principle, this is a way to make a good solid state refrigerator or heater or generator with no moving parts. Now, the problem is that this effect is very nice, but it's usually very small in magnitude. And because of that, it gets limited to sort of niche applications. Things like making a good thermometer. So this is the way to make a cheap thermometer. You just make two dissimilar metals, and they stick together at a junction. And now you put that into something, and by the appearance of a voltage between the two metals, you can detect the temperature. These are called thermocouples. You can also just use it as a probe of your material, saying, OK, well, the sign of the voltage that appears tells you whether your carriers are electrons or holes, whether they have negative or positive charge. And finally, you can actually use it honestly as a generator or a refrigerator if it's in some application where you absolutely can't have it need to be serviced ever. So like if you're in a satellite and you need a refrigerator inside your satellite that has absolutely no moving parts that can fail, then you use the thermoelectric effect. But usually it's not efficient enough to use it, say, to replace your refrigerator at home or to generate power out of some power plant. So let me talk about why it's so hard to make the thermoelectric effect very efficient. And if you have some setup like this, where again I have this couple between a p-type and an n-type material, and now I imagine putting a load resistor that I can tune to try to get as much efficiency as possible, what you'll find is that the efficiency you can get from this device depends only on a single dimensionless number that's called the figure of merit, which we always write as ZT. ZT is proportional to the thermal power squared, basically because whatever power you get out of this will be proportional to a voltage squared, and voltage is proportional to the thermal power. It's proportional to the temperature, because you want large heat current, and the heat current is always proportional to the temperature. It's inverse to resistivity, because if your material has a large resistivity, then you'll lose all power you generate just to Joule heating inside your material. And finally, it's inverse to the thermal conductivity, because if your thermal conductivity is large, you'll be unable to maintain a large temperature difference across your sample, and the temperature difference is what drives the whole effect. And in particular, if you sort of play the game of imagining this setup and now tuning your resistance to sort of be optimal in terms of efficiency, what you'll find is the maximum efficiency you can get, defined as the electric power you extract to the heat flow that came through the device, is this thing, the TH minus TC over TH. This is the temperature of the hot side minus cold side over the hot side. You might recognize this ratio from the Carnot cycle. This is the maximal efficiency that any thermal cycle can have. And it's multiplied by some function, a dimensionless function of a dimensionless number. And if you write out that function, it looks like this. This goes to 1. This efficiency goes to 1 as ZT goes to infinity, but it goes there quite slowly. So that in practical terms, that even if this number ZT is 1, you have something that looks like 10% efficiency. So in general, our efficiency is limited, and the name of the game is to try to make this number ZT as big as possible. All right, so I want to talk to you about how to get big ZT. But first, let me tell you about I want to talk to you about things that make good thermoelectrics, but I should first tell you what makes a bad thermoelectric. And metals are bad thermoelectrics. So let me just go back and rewrite this object in a slightly different way. So what I've done here is instead of writing the resistivity in the denominator, I've written the conductivity in the numerator, and I've factored out units of Kb over E, Kb being Boltzmann constant and E the electron charge. And what you're looking at now is a combination of two dimensionless objects. So this thing here is the thermal power divided by its natural unit Kb over E squared. And this thing is the ratio between the electrical and thermal conductivities. And those of you in physics might recognize this from the Wiedemann-Franz law. So when you have a Fermi liquid, like a normal electron gas, this object is just 3 over pi squared. And the reason is that anytime you have electrons carrying electric conductivity, they can also carry heat. And in fact, they carry heat in such a way that this ratio is just a constant 3 over pi squared, an order 1 number. Okay? So in a metal, making large making a large ZT comes down to how big the thermal power can be. And when you think about it for a little bit, you realize that the thermal power in a metal is quite small, and the reason is that metals have very low entropy. The way to think about this is to draw out the Fermi function, which tells you the probability of an electron state being filled as a function of energy. What you see is that all the states way below the Fermi energy are definitely filled, and they provide you with no entropy. And all the states way above the Fermi energy are definitely empty, and your only freedom to rearrange states comes from a narrow window kBt around the Fermi energy. So consequently, the entropy and therefore the thermal power are both of order T over E Fermi. And in a good metal, E Fermi is generally the equivalent of like 10,000 Kelvin. So this number will be very small, and it's a non-starter. And you'll never make a good thermoelectric just using a metal. So for that reason, any real thermoelectric devices are made from semiconductors, where you can make the Fermi energy relatively small by controlling how many electrons are in your material. Okay. Now I should mention that I sort of said that this object here, sigma over kappa, is in the best case is 3 over pi squared. But in fact, things besides electrons can contribute to the thermal conductivity. You can have phonon contribution, so contribution just from lattice vibrations to the thermal conductivity. So this object should be thought of as, at best, 3 over pi squared, but it can certainly be smaller. And in fact, in semiconductors, it usually is smaller, at least at low density. But let me be optimistic for a minute and just assume, best case scenario, this is an order 1 number. And let's think about how big the thermal power can be. OK, so if you introduce lots of electrons into your semiconductor, you dope it very heavily, then your thermal power, your Seebeck coefficient, will go back to being of order T over E Fermi. So your ZT will be less than T over E Fermi squared. It sort of acts the same as a metal. And this thing is kind of small. Now you can imagine reducing the Fermi energy, so adding fewer electrons. This Fermi energy will start to fall. At some point, it will become smaller than kBt. If it becomes smaller than kBt, then you can sort of forget about quantum mechanics. And you can say, well, my electrons are just kind of like an ideal gas of particles flying all over the place. And now you can think, well, what's the entropy of an ideal gas? And the entropy of an ideal gas is sort of order 1, order kb per particle. Right? It's 3/2 kb times some log. But roughly speaking, the entropy is an order 1 number, which means that my ZT can maybe get to be an order 1 number. Now, if I add even fewer electrons, what happens is those electrons I've added start to get localized. My material becomes an insulator, or in the language of semiconductors, you say the Fermi energy falls into the band gap. And once the Fermi energy falls into the band gap, my conductivity is exponentially small, and my ZT will be exponentially small. Okay? So you imagine playing the game of moving the Fermi energy around. And the point is that when the Fermi energy is high, you lose. When the Fermi energy is low, you lose. And somewhere in the middle, you can hope to get an order 1 number for your figure of merit. And so for that reason, progress in thermoelectrics has historically been quite slow. So this is the plot of the maximum value of ZT as a function of year. This is spanning 60 years. You're going from, say, 0.5 to 2.5. For those of us used to Moore's law, this is a very annoying graph, showing a very slow progression in figure of merit. And I should note, in fact, that all these data points aren't even taken at some standardized temperature. They're taken at whichever temperature gave you the most publishable paper. So this is kind of a frustrating situation. And it's for this reason that I told you that as you play the game of changing the Fermi energy and being optimistic about thermal conductivity, you can hope to get some order 1 number, and that's it. And it's all a game of order 1 numbers. Yeah?
Singularity, like at the end of the band, like there should be some kind of a peak in the density of state, right?
Yeah, so a peak in the density of states can sort of give your carriers lots of entropy, but they can't have more entropy than an ideal gas. That's sort of the point. That an ideal gas sort of represents the upper bound for how much entropy you can have per electron. OK, so I want to talk in this talk about not metals and semiconductors, but about a new class of materials that are called the nodal semimetals. So by nodal semimetal, I mean that you have an empty band, an electron band, and a filled band, a hole band, that meet in momentum space at a point or a low-dimensional set of points in momentum space. So these objects are sort of intermediate between metals and semiconductors. They're like metals in the sense that they have no band gap. And they're like semiconductors in the sense that there's 0 density of states exactly at the band touching point. So without introducing any electrons, your density of states vanishes the way it would in an insulator, but without any gap. Now, of course, at this point, we have lots of such objects. These are the 3-dimensional Dirac and Weyl semimetals. I'm going to stick to 3D, because if ever you want to make a useful device, it's got to be 3-dimensional. And it's funny to think that these things were first discovered only, first announced experimentally only, in the end of 2013, and now we have just a booming industry of finding these materials and exploring their properties. These were the first ones: cadmium-3 arsenic, arsenic-2, and sodium-3 bismuth. And you can study by, say, ARPAS, by photoemission spectroscopy, what their dispersion looks like, or what the energy of the electron as a function of momentum looks like. And you see this nice cone of energy states. In a sense, this is like a photon-like electron that moves at constant velocity in all directions and has no rest mass energy. So there's a whole industry of finding these materials and studying them. I'm going to talk in this talk about two in particular, which are zirconium, telluride, and tantalum phosphide. OK, so let's talk about the thermopower of such materials. And in particular, let's start by thinking about the thermopower of semimetals, which means materials where you can simultaneously have electrons and holes. And when you first look at this problem, it looks like a bad idea, because the sort of benefit of a semimetal is that it can have both electrons and holes at the same time. But now if you think about running the thermoelectric effect with electrons and holes present simultaneously, you realize that they cancel each other. So in particular, imagine operating the thermoelectric effect in refrigerator mode, which means I apply an electric current and hope to get a large heat current. But the problem is that if I'm running an electric current, say, to the right, that means the electrons are going to the left and the holes are going to the right, which means they're canceling each other in the heat current. One is carrying heat current left and one carrying heat current right. So when you make this ratio, heat current over electric current, it gets small, they cancel. So you can think about it, if you play the game of, again, changing the Fermi energy, you find that at high Fermi energy, this thing behaves like a metal. The thermopower is T over E Fermi. As I lower the Fermi energy, it starts to go up until I get to the point where the Fermi energy is comparable to the thermal energy kBT. And then I'll start to excite holes in the valence band. And those holes will cancel the electrons, and I'll have to go back to 0. Right? So again, it looks like I can get some order 1 number for the thermopower and not better. All right, so the point is that if you want to do something better than just having electrons and holes cancel each other, you need to find a way to make electrons and holes work together, to make them contribute additively to the thermopower. And this is where the first important idea comes in. And that idea is that you can make electrons and holes move in the same direction if they're under the influence of a strong magnetic field. So in particular, imagine that I have this material and I apply a very strong magnetic field, strong meaning that the carriers complete many cyclotron orbits before scattering off of some impurity. Now, in that configuration, you can say that I have large Hall angle, which means that the electric field mostly points perpendicularly to the direction of current. And now I have electrons and holes sitting in crossed electric and magnetic fields. Okay? Now you can think back to whatever was your favorite course on electromagnetism. And remember, when you have particles in crossed electric and magnetic fields, they move by what's called the E cross B drift, which means they drift in the direction of E cross B. And the great thing about the E cross B drift is that it points in the same direction regardless of the sign of your charge. So electrons will do clockwise spirals, and holes will make counterclockwise spirals, but they'll both drift in the same direction, which is the direction of E cross B. Okay? So now if you want to think about, well, what's the thermopower in this situation? Well, I should again make the ratio of the heat current to the electric current. The electric current is just this E cross B drift velocity times the number of holes minus number of electrons. See here, they're carrying electric current in opposite directions. But they're carrying heat current in the same direction. And I can think about the heat current by saying, OK, if the current is flowing transverse to the electric field, then I can think of this as a reversible process, a thermodynamically reversible process. And in thermodynamics, we have a relation that for reversible processes, the heat current is related to the entropy current by this relation. JQ is T times JS. And the entropy current here is just that same E cross B drift velocity times the total entropy of electrons plus the total entropy of holes. So in the end, by making the ratio, I come to this very nice formula, which says that in this regime of large magnetic field, the thermopower is just the total entropy electrons plus holes divided by the net charge electrons minus holes. So in this sense, I've got what I wanted. I've got an addition in the numerator and cancellation in the denominator, and they're working together to give me a large thermoelectric effect. Now, a magnetic field does another really nice thing for you, which is that it sort of changes the quantum mechanical nature of electron trajectories. So at zero magnetic field, we sort of think that electrons are flying all around in all directions. But at large magnetic field, they're constrained to make very tight cyclotron orbits. And when the size of those cyclotron orbits becomes smaller than the typical spacing between electrons, you reach what's called the extreme quantum limit, where basically all the motion of the electrons perpendicular to the magnetic field is locked into the same quantum state, the same lowest Landau level. Now, you would think that that sort of removes entropy from the system, and it does. But fortunately, you still retain lots of entropy associated with electrons drifting in the z direction. So they feel no Lorentz force when they're drifting in the direction of the magnetic field. And because of that, they can retain lots of entropy associated with motion in that direction. So once you reach this extreme quantum limit, the limit where you have only one Landau level of cyclotron motion populated by the electrons, you start to change the density of states of your system. So in particular, imagine that I have some material, I turn on the magnetic field, and once I reach this limit where all electrons are sitting in the lowest Landau level, I can count my density of states sort of by counting the number of quantum of magnetic flux that pass through my system. So quantum mechanics tells us you should have one quantum state per motion in the z direction, per momentum in the z direction, and per quantum of magnetic flux. So I can sort of divide my system into tubes, each one containing some number of flux quanta. Each one containing one flux quantum. And now I say, well, each tube gives me some density of states. It turns out for a 3D Dirac or Weyl semimetal, that density of states is just a constant. And I get a constant amount of density of states per quantum of magnetic flux, which means the total density of states is growing like B, proportional to magnetic field. That means that the Fermi energy must be going down. If the density of states is going up and I have a fixed number of carriers, the Fermi energy will drop. And as the Fermi energy drops, that means that the thermal power has to rise. Thermal power, which looks like T over E Fermi. Okay, so here's a calculation. This is essentially just a calculation of the electronic entropy as a function of magnetic field. And what you're seeing is that at small magnetic field, this thing just behaves like a metal. It has a thermal power of order T over E Fermi. As I turn up the magnetic field, I start to see oscillations, and these are your peaks in the density of states associated with Landau levels moving through the Fermi level. Finally, I reach the situation where all electrons occupy only the lowest Landau level, and that's here, what we call the extreme quantum limit. And once I hit that, the thermal power starts to rise because I'm driving the Fermi energy down. And now, as I drive the Fermi energy down further and further, eventually I get to a point where the Fermi energy is smaller than kBt. So I start to have thermal excitation of both electrons and holes simultaneously. And the amazing thing is that as I turn up the magnetic field higher, I get a proliferation of all these electrons and holes, and they all add in the same way to the thermal power. So rather than canceling each other, they add together. I turn up the magnetic field higher and higher. I get ever more electrons and holes because I have higher and higher density of states. So the thermal power is allowed to just keep rising and rising and rising without saturation.
So I got confused here that where this work comes from, that you're sitting at finite bias, a finite density starting with. Right?
Yeah, I have a fixed density of electrons. Electrons minus holes is fixed.
And then at the extreme large magnetic field, that you have now just one Nodal level remains in the
Yes.
direction and the directions, right?
Yes.
But still, all the characteristics still kind of I view that this is electron Nodal.
Right. So what happens is I have two bands like this, right? So as I turn up the magnetic field, I move this Fermi level down. Right. The Fermi level sinks with increasing magnetic field. Right. The Fermi level is sort of determined.
That's a part that I got probably confused and don't understand.
Yeah.
Already on the magnetic field, I cannot think about this kind of continuous dispersions, right? Basically, I have a set of Landau levels.
Yeah, you have a set of Landau levels, right? So what I'm plotting, I guess, is the maximum value of kz in the lowest Landau level, and that's what can sink as I.
I see. Okay. Yeah. Dispersion. I see. Okay.
Yeah, sorry. You can think of this is dispersion in the lowest Landau level as a function of kz, and then I have higher Landau levels, of course. So this is kz. I have higher Landau levels up here, but at this high enough field, I don't care about them. But as I turn up the magnetic field, the degeneracy of the lowest Landau is increasing. So the Fermi level, in terms of occupation of the lowest Landau level, can go down. And as it comes closer and closer to 0, at this point, I start to get lots of thermal excitations of electrons and holes. And all those electrons and holes act as carriers of thermal power in the same direction. That's the idea. Does that make sense? Okay. Yeah.
In real materials, the Fermi levels start somewhere with respect to the Weyl point, right?
Right.
So it's a question of like how long does it take to get there?
Yeah, indeed. So I'll come to that question in detail in a second. But the point is indeed that you need something with a relatively low Fermi level to start with, so that by applying a modest magnetic field, you can already start to get this effect.
But if I just kind of think about it in that way, for example, I can think about just nanotube, like this, just metallic nanotube.
Yeah.
Just kind of this linear dispersion relation, one dimensions, and just a few of the impurities. But I don't expect it to make thermal powers diverse out in the nanotube, right? So what's so special here?
So what's very special here is this Lorentz force. You need this Lorentz force to make electrons and holes drift in the same direction. And I'll also show you need three dimensionality so that your carriers can retain entropy associated with drifting in the third direction. So without the ability to drift in the field direction, you lose all your entropy and your thermal power drops. So you need both things. Yeah.
On the previous slide,
Yeah.
like where you have PNP, what is the SXX measurement?
So this is just a pure theory calculation. And
So
you mean what is the meaning of the thermal power? Yeah, this is literally like I apply a temperature gradient along some direction perpendicular to the magnetic field, and I measure the resulting voltage in that same direction.
so SXX is just RXX.
It's the response.
VXX.
Yeah, it's VXX over delta TXX.
Okay.
Yeah. Or VX over delta TX. Yeah. Okay. So actually, after we did this calculation, we found this older paper from Huanong's group, and buried in the bottom of the paper was exactly a measurement that looked like what I just showed you. At low magnetic field, you see some oscillations, and then you have a dip before you reach the extreme quantum limit, and then it starts to grow linearly as a function of the magnetic field. So this is a sort of Dirac semimetal lead tin selenide. And I think what was not appreciated by the authors at the time is that this growth can just keep happening. And in this particular material, it took 10 Tesla to start to see it, like for the reason you said, the Fermi energy was relatively high here. But what they perhaps didn't appreciate is that if you find a material with a lower Fermi energy, or you can go to larger magnetic field or larger temperature, there's no reason why this just can't keep growing and surpass the bounds of what's possible in semiconductors. Okay, so let me just make a comment about numerical estimates. Let me stick for the moment to this same material, lead tin selenide. And what I'm going to do is I'm going to try to estimate this ZT using the thermal power from our theory, and just take this ratio T over rho times kappa as an experimental given. So I said if you're very lucky, then T over rho times kappa is order 1. Turns out usually you're not very lucky, and kappa is dominated by phonons. You have lots of phonon contribution to the thermal conductivity. So let me just look up from literature what the resistivity is and what the thermal conductivity is and plug it in. And this is sort of what I get. So for the same material, I see ZT is something, okay, it looks bad, 10 to the minus 7. But I have a T in Kelvin squared and a B in Tesla squared. So if I imagine making a material with, say, 10 to the 17 carriers per cubic centimeter, then at room temperature and 30 Tesla, I can hope to get ZT equal 10. So just to make a point, here's historical progress and here's 10. So this is potentially a big deal. It's just a way to see something that hasn't been seen before. Now, okay, you can certainly balk at the idea of making a generator or refrigerator that only works in a 30 Tesla field. And for that, like you said, you want to be able to get this N down. If you can make the carrier density lower and lower, which means the Fermi energy is lower and lower, then you can start to see this effect already at reasonable magnetic fields. So in particular, if I can get down to, say, 10 to the 15 carriers per cubic centimeter, which is clean, but not like silicon grade clean, then you could already start to see this effect, or hope to see it at least, at 1 Tesla. So now you can hope to just have some internal magnetization, or say a neodymium magnet sitting on top of it, and already have some useful thermoelectric. Okay, so let me just make a conceptual recap of what happened here. So I gave you this very generic argument of why conventional materials are not allowed to have thermal power much bigger than kB over E. And I told you there's a way around that. And really, this way around it sort of comes down to a miraculous confluence of 3 different things. One is the large magnetic field enables this E cross B drift that allows electrons and holes to work together in the way they carry heat. The second one is that turning on a large magnetic field increases your density of states and drives down the Fermi energy without killing the electron entropy. So that's very important that the carriers retain entropy associated with their drift in the Z direction. And finally, because of my gapless band structure, I have some kind of electron-hole symmetry, which guarantees for me that as I turn up the magnetic field higher and the Fermi energy falls, it will sort of stick to 0 where I have an electron-hole degeneracy point. And that allows any given finite kBt to create lots of electrons and holes. This would be different in a conventional semimetal where I have no such symmetry between electron and hole band. They say exist in different parts of momentum space. And as I turn up the field very high, the chemical potential will just stick to one of the 2 bands. And I'll have one carrier type and the others will be dried out. But this ability to create electrons and holes simultaneously allows me, as I turn up the magnetic field, to sort of create ever more electrons and holes, and they all add together to the thermal power, and it can just keep growing. So you really need all 3 of these things. If you take away any 3 of these ingredients, you'll lose the ability to make a non-saturating thermal power. So just to show that, imagine taking a conventional semiconductor where I really have only one band to think about. And you'll see something that looks kind of similar at first, a small thermal power T over E Fermi. Start to see some oscillations associated with Landau quantization. For anyone looking really closely, there's a spin splitting that you're seeing here of some Landau level. And then at very large magnetic field, I'll start to drive it up as I drive the Fermi energy down. But eventually, I'll get to a point where the Fermi energy becomes smaller than kBt, my electrons sort of become ideal gas particles, and then there's a saturation of the thermal power. Basically because I have a fixed number of electrons. And without the ability to create ever more carriers with increasing magnetic field, my thermal power has to saturate. Okay, so you can look at it there's a easy objection to make, which I'm telling you that, well, I have an effect that becomes very strong when you're very close to charge neutrality, when the net concentration of electrons minus holes becomes small. But now you can worry that, if I bring that exactly to 0, the thermal power has to vanish by symmetry. It can't be either positive or negative in sign, so it has to vanish. So without magnetic field, I sort of told you the thermal power sort of goes up to some order 1 number and then comes back to 0 where the electrons and holes cancel. And then I told you that with magnetic field, I can have something that diverges as I make the carrier density 0. And you can be worried about that. But the solution to the problem is basically that I gave you a derivation that required a large ratio between the Hall conductivity and the longitudinal conductivity. I told you that the electric field is mostly transverse to the current. And if you have exactly equal number of electrons and holes, there's no way to have that condition, that your Hall voltage will vanish. And if you work through it, what you'll find is that you need to have this condition of large transverse conductivity, you need omega c tau, the number of completed cyclotron orbits before scattering, to be bigger than the concentration of electrons plus holes divided by electrons minus holes. Okay? So if you work out what it means for this plot, it basically means that as you reduce the Fermi energy, you will again have a sort of a peak and then dropping back to 0. But the position of this peak is not at kBt anymore. It's at the much smaller Fermi energy kBt over omega c tau. So your maximum thermal power is not order 1, it's order omega c tau. It's limited by how big you can make your magnetic field and how high the mobility can be. Okay. So let's move to the experimental part of the talk. If you have theoretical objections, you should make them now. Otherwise, yeah.
I was just wondering, once you've confined your electric poles to these trajectories, do you expect at some point that they can undergo sort of transverse phase? Like, for instance, once you put interaction, you can get transitions that
Right. So actually, this is what you're hitting on a long question, a long studied question, which is the idea that, in some sense, I'm sort of giving you this picture where electron trajectories have sort of become one-dimensional, which should make them susceptible to any kind of instabilities. And there's a long literature of looking for those instabilities. And I'm sort of circumventing it by saying, well, I care about larger temperature anyway. But in principle, at low enough temperature, you do have some kind of instability driven by interactions, or at very least by disorder or something. Okay. So let me go into the experimental part. I want to talk to you about two materials. The first is zirconium telluride, and let me introduce you to it. Zirconium telluride is a sort of a layered material that has zirconium and tellurium. It grows in sort of long ribbons or flakes that you can grow at sort of centimeter scale and maybe a few, half a millimeter thick. The nice thing about its band structure is it sort of lies at the boundary between a topological insulator and a trivial insulator. So as you tune some parameter, you can go from a trivial insulator, which has a band gap, to a topological insulator, which has a band gap plus surface states. But exactly at the band inversion point, your conduction and valence bands meet, and they touch at a point. And this material sort of lies right at that special point. And it's just very sensitively dependent on the lattice constant of whether you have a gap or how big the gap can be. So photo emission studies has sort of shown that you do have a cone. They disagree about whether there's a gap, but if there is a gap, it seems to be smaller than 20 millivolts. So there may be a gap, but it's a very small one. The nice thing about it from a practical perspective is that the carrier density here is very low. So you can make these samples very clean, and our collaborators grow them very clean. So you have something like 10 to the 16 electrons per cubic centimeter, which is already smaller than the number I suggested could give you figure of merit 10. And it has very high mobility, so 600,000. So the nice thing about this huge mobility is that it allows you to see quantum effects already a very small magnetic field. So here you're seeing just resistivity as a function of field, and these oscillations tell you about the development of well-formed Landau levels. And you start to see them already about 0.1 Tesla. And the nice thing is because of the low carrier density and, in fact, exploiting the anisotropic velocity, you can get the system into the extreme quantum limit already starting around 1 Tesla. So this is entrance into the very last Landau level. So starting from here onward, you should start to see enhancement of the thermal power, already at 1 Tesla. OK, sorry. I can't resist to just mentioning that the same material, zirconium telluride, is sort of at the center of a pretty amazing claim of quantized electrical conductance in 3D. So this is something like quantum Hall effect. Oh.
So what is the temperature dependence? I'm saying partly from a money-making point of view, is that the conventional thermoelectrics don't operate, they don't cool
Yeah.
those red detectors very well.
Right. I'm going to get to the temperature dependence in a second, and what you'll. The answer is no. They don't. They work really well at up to about 50 Kelvin, and then they start to work less well above 50 Kelvin.
Oh, but that's incredible.
Okay, so let me just skip this, and I'll get to that in a second. This is sort of a side claim, just saying this material is exciting for other reasons. But oh, sorry, I did this in a funny order. Let me first introduce you to the other material I care about, which is tantalum phosphide. So tantalum phosphide, Ming-Dao Li's group over here grows them in centimeter-sized single crystals. These are relatively isotropic. And in fact, they're Weyl semimetals rather than Dirac. And a Weyl semimetal is sort of protected from opening any gaps. So you sort of know that you have these nodal points with no gaps in them. And in fact, it has not just two such points. It has 24 points. And actually, the existence of a large degeneracy helps us in this sense, because large degeneracy means you have lots of entropy. So in fact, there are sort of two inequivalent types of Weyl points that are separated in energy by about 50 millivolts. As I understand, the difference between here and here is about 50 millivolts. And your chemical potential lies somewhere in between them. So you sort of have it simultaneously intersecting a hole band and an electron band. So the nice thing about this from our perspective is that it can be made with a similarly very low charge density and a very high mobility. Right, and so you can see evidence of the high mobility just by looking at transport. And here you're seeing resistance as a function of field. And if you can just look at the lowest temperature curve here, you're seeing lots of these oscillations down to, say, 1 Tesla or so, which is an evidence of high mobility and that these quantum effects are very present. In fact, if you look at the data really closely, you can find that it doesn't just look like a single period oscillation, that there's sort of multiple periods in here. And you can say, look at it as a function of 1 over b. And you see that there are 2 different periodicities here. And what it eventually tells you is that this is what you'd expect from this picture I showed you before, that you have one pocket of carriers associated with what are called the W2 Weyl points, and another pocket associated with the W1 Weyl points. And so you're seeing both of these Fermi surfaces simultaneously in the transport data. And what it comes down to is that in the samples that they studied, the Weyl node, the chemical potential happens to be closer to the Weyl node W2, and in fact only, say, 2 to 3 millivolts away. And if you make an estimate, you find that the carriers in this Weyl node W2 enter the extreme quantum limit already starting at about 1 Tesla. So already at 1 Tesla, you start to see the physics we care about. Unfortunately, it's further away from the Weyl node W1 and seems to require as much as 20 Tesla, and we're not quite there yet. Okay, that's the situation. So now let's talk about how it looks for thermal power. So we have these two candidates that are sort of good, two materials that are good candidates for seeing this huge enhancement of thermal power. So here's our prediction. The only thing you really need to know for the moment is that the thermal power should grow linearly in temperature and linear in magnetic field. So here's the data for zirconium telluride. Here I'm showing you low temperature. And what you're seeing is something that's sort of growing, sort of linearly with magnetic field. And the slope of the linear slope is increasing with temperature. And that's good. That's what we want. So just to make a point, here's our theory prediction for 40 Kelvin. It looks reasonably good. The slope is reasonably close. And I should make a point that getting to 400 microvolts per Kelvin at 40 Kelvin is not easy. So the unit kb over E is 86. It's down here. And so now we're already 6 times above that at this cryogenic temperature, 40 Kelvin. That's sort of a big deal. Now the problem is that as you turn up the temperature higher, this slope is supposed to just keep getting higher, but it doesn't. Unfortunately, starting around 60, 80 Kelvin, that slope starts to narrow off, and a really funny and annoying thing happens, which is that the thermal power actually switches sign. It goes from N-type to P-type. And that's kind of unfortunate, right? The thermal power is supposed to just tell you whether your carriers are electrons or holes. And supposedly, as you change the temperature and as you change the magnetic field, your carriers switch from hole type to electron type. And that ends up sort of killing this effect that we wanted. Now, it turns out that this is sort of known in zirconium telluride, that as you increase the temperature, your carriers switch from N-type to P-type. So these are sort of photo emission studies. And what you're seeing is that the Fermi level moves relative to the Dirac point as a function of temperature. So at low temperature, it looks N-type, and then it moves down into the hole band. It looks P-type. The way that this is typically explained is that you have somewhere in momentum space, you have another heavy electron band that's sort of close to the Dirac point. So this band, by virtue of being heavy, doesn't really contribute to transport, but it has a large density of states that can suck carriers away. So as you increase the temperature, those sort of carriers that were near your Dirac point sort of get thermally excited into this heavy band, and you don't see them because the band is so heavy. All you see is something that looks like just a movement of a shift of carrier type in the Dirac band. Yeah.
Can you talk about what the trajectories would look like in real space? Are these
This is all bulk phenomenon. Everything here is bulk.
Okay.
So you can think that you have, in the field direction, your carriers are sort of making cyclotron orbits and drifting back and forth. And then because of the cross electromagnetic fields, those trajectories are also drifting in the longitudinal direction. Yeah. OK. So anyway, so this effect exists in this material zirconium telluride. And in our purpose, what it means is that this nice linear enhancement of thermal power is sort of messed up. And you can see that this evolution of the carrier type with temperature and magnetic field, it's also reflected in the behavior of the Hall resistance. So you see at low temperature, it looks N-type, and then it switches to P-type. And you have this weird nonlinearity that suggests evolution of the carrier type with magnetic field as well. And you can think about that just because, at high magnetic field, the bottom of this heavy band shifts a little bit. It shifts by 1/2 h omega up and allows you to have more of your carriers come back here. Anyway. OK, so let's look at tantalum phosphide. Now, here's the same form. So we have another factor. We have a large factor here that comes from having many Weyl points that helps. And here I'm just showing data for 50 Kelvin. You can tell I've covered something up. Don't worry, I'll reveal in a second. And here you're seeing this large linear enhancement of the thermal power with magnetic field. And that's exciting. And look at the magnitude here. Sorry, there's a 10 to the 3 here, which I don't want you to miss. This suggests you're already at 1,000 microvolts per Kelvin. Down at 50 Kelvin, and that's huge. Remembering that kB over E is here. So this is a very large thermal power at a very small temperature, and that's impressive. Unfortunately, OK, so sorry. Here's the theory curve, and it matches even better than one could hope for. The problem, of course, is what happens at higher temperature, and what you see again is that you go from low temperature, which are these blue curves, and the slope of the thermal power comes up the way it's supposed to. And then when you get to about 50 Kelvin, it starts to dive again. And actually, if you look really closely, 0 is here. So at room temperature, you've again switched the sign of the thermal power. And it goes from N-type to P-type again. So again, the temperature dependence is not simple here. And particularly above 50 Kelvin, something happens, and your carriers are switching sign, and it's ruining the thermal power.
It's also where the thermal conductivity shows a peak in 50 Kelvin.
Yeah, somewhere around 50 Kelvin, you see the peak in the thermal conductivity as well. So again, you can yeah.
That's not bad at all, because the commercial problem is you take the old-fashioned thermoelectrics and you want them to cool some detector, and the colder it gets, more sensitive it gets.
Yeah.
And the old ones tend to die at like 100K or
right.
higher than that.
Yeah.
And which is a big problem.
Right.
And so if you can actually fill in it.
Yeah. So. Yeah, so in a sense, and this might all be good in the end for low temperature thermoelectric cooling, which might be a big deal. Unfortunately, this material, tantalum phosphide, has a huge thermal conductivity, which makes the figure of merit pretty small. But the power factor is very big. So anyway, there's promise here. There's real promise. But I don't want to sell something ready for market yet. OK, and again, sort of one of the problems here is that you have these two carriers. So as you turn on the temperature, you can sort of have activation of carriers from one band to another, and they're sort of partially canceling each other. I mean, in the sense that your carrier number can evolve in a non-trivial way as a function of temperature. And you can see that again from just looking at the data for rho xy. Here is just a sort of a two-band model fit, and that shows you that whether you have more electrons or more holes depends on temperature, because your carriers are sort of redistributing between the two bands as a function of temperature. So not only do you have this evolution of the carrier density with temperature and magnetic field, you can sort of, because you go through a point where holes and electrons are sort of equally abundant, you can easily lose the condition of large Hall conductivity, even though you have large omega c tau. So even though you have something that's relatively clean, electrons are completing many cyclotron orbits, once you lose this condition of large sigma xy, you lose the criterion for this linearly growing thermal power. So this is what you'd like is to see some interesting effect anytime you have this criterion, even without requiring that one. So that's when we decided to look for sort of a simpler quantity to look at, and we hit upon the thermoelectric Hall conductivity. So if you want, this Seebeck coefficient, this thermal power, is sort of like a longitudinal resistance in the sense that you apply a temperature gradient and you measure a voltage in the same direction. And we thought, well, maybe it's easier to look at something that looks like a thermoelectric conductivity, right? So in particular, I'm going to now switch to talk about thermoelectric conductivity alpha, which is defined as basically you apply a temperature gradient and you ask how much electric current do you get out of it. Or similarly, you apply an electric field and ask how much heat current do you get out of it. And I'm going to look at the transverse coefficient, so the transverse thermoelectric conductivity, or the thermoelectric Hall conductivity, which you can think of from the second equation as the ratio between the heat current and the electric field that you apply in the perpendicular direction. Now, our motivation for looking at this transverse thermoelectric conductivity is really kind of simple. And our inspiration was sort of the quantum Hall effect, which in the quantum Hall effect, sorry, you probably can't see this very well. The longitudinal resistance is really messy and has a million wiggles and bumps. But the transverse conductivity is very simple. It just looks like a series of steps, a series of plateaux. So our thinking was that maybe similarly, you could expect this transverse thermoelectric conductivity to have some simple behavior, even though this longitudinal thermal power is doing something messy. So there's a relationship between the thermal power and the thermoelectric conductivity. One is just this is just the resistivity tensor times the thermoelectric conductivity, and in particular, the thermal power in the limit of large magnetic field is just alpha xy divided by sigma xy. So we know that the sigma xy is really messy, that it has, the carrier concentration is changing with magnetic field and with temperature. But maybe there's a hope that all the messiness isn't here and that sigma xy, alpha xy can still be simple. Okay. In the interest of time, maybe I don't want to spend too much time on this, but we were sort of taught mostly, as far as I understand, mostly by Bert Halpern in the 1980s, that the transport properties of, say, the quantum Hall effect can be understood in terms of the edge states. So that you have in the bulk these sort of Landau levels that electrons occupy, and near the surfaces of your material, those Landau levels sort of bend upward, and all the transport comes from the part where this edge state intersects the side of your sample, right? So this, and you can understand, basically on this side of the sample, you have sort of current going into the board, and on that side you have current going out of the board. So if you want to understand the conductivity, you can say, well, I apply an electric field in this direction, then now biases the chemical potential, so I have a few more states over here than states over here. And then you can understand everything just from thinking about those edge states. Similarly, it was figured out pretty soon after that you can understand the thermoelectric properties of the quantum Hall effect in a similar way, that these edge states are what's carrying your heat current. And if you just do the calculation and find out, well, what is alpha xy for that coming from these edge states, you'll find that it's just some universal number e over h, that's the unit of alpha xy in 2 dimensions, times an integer that's like the number of bulk Landau levels intersecting the chemical potential. Okay, so if I draw the chemical potential, say here, in between the Landau levels, I'll find that alpha xy is very small, it goes to 0. Whereas if it's sort of in the middle of Landau level and intersecting it, then this becomes e over h times some order 1 number. Now we can do the same calculation in 3 dimensions. The difference for our problem is that, first of all, we have another momentum in the z direction. Our surface states are not just lines, they're sort of planes. Plus our band structure looks a little different. We sort of have this lowest Landau level that's electron hole symmetric, and that splits up in one direction and down in another. So no matter where you put your chemical potential, you'll always have some edge states intersecting it. Okay, you do the same calculation here, and what you find, first of all, because this is a 3D conductivity, you need a momentum scale. And that momentum scale basically comes down to t over the Fermi velocity. This is a momentum, it's proportional to t. Basically tells you the width and momentum space around which your states are partially occupied around the Fermi level.
So these Fermi states are along the z direction?
Yes, and this Fermi velocity along the field direction, indeed. And then you have this some integer number that's like the number of bulk Landau levels intersecting the chemical potential. Now in 3D, your Landau levels sort of have this funny structure. They sort of look like, I don't know, cylinders or something that sort of increase in diameter as you turn up the magnetic field. But the point is that you're, unlike in 2D where you can have a chemical potential in between Landau levels, in 3D your chemical potential is always intersecting some number of Landau levels. So this thing never goes to 0. It's always finite, this alpha xy. Okay. So now what this implies is that in the limit of small magnetic field where many Landau levels are occupied, your quantity alpha xy, it's proportional to t always, so I take a t out here. It looks like this quantity right here, which is just the number of occupied Landau levels. It depends on how many electrons you have. It depends on the magnetic field. But when I turn up the magnetic field very high, such that only the lowest Landau level is occupied, I get this very nice result where alpha xy over t is just something, some universal constants here, a factor of the Fermi velocity, times some number that just tells you the degeneracy of the Dirac point. So it's just an integer that tells you the degeneracy of the zero energy point. So in this sense, this alpha xy over t becomes quantized. And I want to make a point that it now becomes completely independent of magnetic field. There's no B. It becomes independent of disorder. There's no scattering time anywhere. It's independent of the electron concentration. There's no N. And it's not even dependent on the sign of the carriers. Electron type or hole type doesn't matter. As long as I stay in the lowest Landau level, all that matters is that I have one edge state or one band intersecting the Fermi level. And it doesn't matter whether the carriers are electrons or holes or how many of them are or what's the magnetic field. So in this sense, it's like a universal plateau in alpha xy. OK, I won't go over this. The point is just that we think about sigma xy, and usually we have a very simple argument for what sigma xy is. We just say, OK, there are a bunch of carriers n, and they're all doing E cross B drift. So in the dissipationless limit, the conductivity is just Ne over B. Right? That's our usual argument for the transverse conductivity. And if you want, you could do the exact same calculation with surface states. You could integrate over all possible surface states, and you'll get the exact same answer for sigma xy. And what that suggests is that there should be a bulk way of thinking about alpha xy. There's a way of thinking about deriving alpha xy by thinking about transfer along surface states, but there should be a heuristic bulk way of doing it too. And the heuristic way is basically just by looking at this definition of alpha xy that involves the ratio of the heat current to the electric field. And you say, again, the heat current is related to the entropy current. The entropy current is related to the density of states. So this object here, T times the density of states, is just the entropy density. And the entropy density is related to the heat current. And now you make the ratio, and you just find that alpha xy over T reflects the density of states. Now, the beautiful thing about Dirac and Weyl materials is that at large magnetic field, the density of states is linear in B and is otherwise energy independent. So this just counts the number of flux quanta in your system, and otherwise it has no dependence on the energy. So this B over here cancels with B over here, and you get this beautiful plateau in alpha xy that comes from the energy independence of the density of states. OK, so here's the theoretical calculation. What you're seeing here is that sort of at small b, you sort of start to ramp up alpha xy, and this just comes from, this is the limit of small omega c tau, if you want. Once you reach the limit of large omega c tau, it starts to come down again. You see some wiggles. But the important part is that at large field, when you reach the extreme quantum limit, you get this plateau in alpha xy. Right. And just to convince you that the same thing does not happen in conventional semiconductors, here's sort of the plot of the same phenomenon. It all looks kind of similar until you get to the extreme quantum limit, in which case this thing continues to evolve with B and still depends on the electron density. And there's no such plateau. OK, now let me show you the results. Here's zirconium telluride. And I just want to make a point here that what I'm plotting here is really a convolution of 4 different measurements of resistivity in the longitudinal and parallel perpendicular directions, and thermal power longitudinal and perpendicular. And all 4 of these objects are kind of complicated. So this thing here is rho xx and has all sorts of magnetoresistance effects that are hard to look at. Rho xy is similarly complicated, changing sign of the slope and funny things happening at high field. Thermal power I already talked to you about is complicated for various ways. But when you look at this ratio, you get something really nice and simple, which looks like this. So here's alpha xy. It sort of falls with field, and then it reaches this plateau, and that plateau now becomes independent of field, independent of temperature once you've made the ratio of alpha xy over T. And so in this sense, it looks like some universal plateau in this thermoelectric Hall conductivity. Just to show you that you take the formula that I showed you before, and you get something that's right about here. There's kind of a large error bar that comes from uncertainty in the Fermi velocity, but it's very consistent with what the data is showing. And so if you want, you can sort of think of this plateau as a test for whether you have a gapless Dirac or Weyl system. And because the magnitude of the plateau depends literally only on the Fermi velocity and nothing else, you can in fact use it to measure the Fermi velocity, and then you could tilt your field in different directions and map out the velocity in different directions. OK, so now let me show you what it looks like in tantalum phosphide. Again, in tantalum phosphide, you sort of have difficult behavior of rho xx and rho xy. And again, the thermal power sort of has this complicated behavior on both temperature and field. But when you make the ratio of this combination of the 4, alpha xy starts to look pretty simple. So here it's coming down for some large value, and it's reaching a plateau. There's sort of still a dispersion among the different curves here. That comes basically because you have 2 different Weyl points. And one of them is deep into the lowest Landau level, deep in the extreme quantum limit. And the other one is still approaching it. So you have one contribution that's plateaued and the other one that's slowly decaying away and allowing you to reach a plateau. So that's sort of what's happening here. The theory prediction is sort of mostly consistent with the plateau value as far as we can tell, although it's not completely plateaued yet. OK, so that's mostly what I wanted to tell you. Let me just put up some conclusions and tell you that what we really have is sort of a new mechanism for achieving very large thermal power, a new pathway. Still unclear whether it will pan out, but there's something very exciting here, using a nodal semimetal in a strong magnetic field. And not only do you have this growth of thermal power, you sort of have this universal plateau in the transverse thermoelectric conductivity. And I'll refer you to the papers here. This is our theory paper, and there are two experimental papers on the archive that I mentioned, both zirconium telluride and tantalum phosphide. And I'll just stop there. Thank you.